Okay, so now we have the hyperbolic ligand equation. We know how we were able to derive this from the law of mass action. So if we have data, for instance, in the form of theta on the y-axis and the initial ligand concentration on the x, we can then plot this, plot data at different ligand concentrations. And then we can fit this equation to this. However, this requires what's called nonlinear regression fitting, because this is a hyperbolic equation. And so, as you're probably more familiar with, you're more familiar with something like linear regression. And in fact, for many decades, that's how a lot of these equilibrium constants and also rate constants were determined, was by linear regression, not nonlinear regression. So this is relatively new in the last couple of decades as programs such as Excel or other nonlinear regression programs have become more powerful and have been developed. So what we need is we need to be able to transform this into something linear to make it easier to fit so that we can extract these parameters. And so one way of doing that for this equation is we want, and just to emphasize what we want, is we want something with the form where we have a y, which is measurable, mx plus b, so that's the linear form. So we have x and y, which are measurable, and we're going to extract m and b from the plot. So if we take the inverse, one way to do this for this is to take the inverse of both the left and the right side. So that means 1 over theta is equal to, and to do the inverse, all we're going to do is we're going to flip the numerator and the denominator. And that gives us ligand naught plus Kd over ligand naught. All right? And now, because there's a plus sign in the numerator, we can separate these into two terms. So one on the left-hand side is ligand naught over ligand naught, which of course cancels out, and we get 1. Second term is Kd over ligand naught, but we're going to write this as Kd times 1 over initial ligand concentration, okay? And so what we get is a final equation where 1 over theta equals 1 over ligand naught times Kd plus 1. And this satisfies our need to have something in the form of y equals mx plus b, because this is y. Y is equal to 1 over theta. X, which is measurable, because this is our ligand concentration, we control for that. That's 1 over ligand. That means m, the slope of the equation, is going to be equal to Kd, and b is just 1 in this case. Okay? So we can convert then, through this equation, we can convert our plot on the left-hand side, this hyperbolic plot, where we change the y and the x-axis. So now the y-axis is 1 over theta instead of just theta. Oops. One over ligand. Okay, is the x-axis. And now we get our points where points at larger ligand concentrations are actually smaller data points now because they're inverted, right? And where there were larger ligand concentrations, they're now at higher numbers. And then we can fit this using standard linear regression that we can do on Excel or a graphing calculator. And the slope, again, as we said, m is kd. And using this linearization technique, we can find, we can more easily find the slope and the kd for ligand binding to a particular protein.